Hey everyone, and welcome to This Explainer. Today, I'm going to be your friendly science teacher and guide as we decode the absolutely fascinating physics behind alternating current. This is the invisible, harmonic motion that powers literally almost everything in our modern world, from the toaster sitting on your kitchen counter to the massive power grid itself. Now, because this topic is just packed with incredible physics and engineering, we're going to treat this like a step-by-step beginner tutorial. We'll follow a clear roadmap today, starting with Part 1, Winning the Current War, then the anatomy of the AC wave, learning the language of phasors, exploring components and phase races, synthesizing the LCR circuit, and finally, transformers, the grid's engine.
All right, let's jump right into Part 1, Winning the Current War, and the triumph of AC. To really understand why our grid uses alternating current today, we first have to look at the massive historical shift that actually made it possible. Back in the day, there was a literal, fiercely fought war of the currents between Thomas Edison, who backed direct current, and brilliant minds like Nikola Tesla and George Westinghouse, who championed alternating current. So, why did AC win? Well, it comes down to the journey. Think of electricity taking a massive road trip from a power plant to your home. Direct current simply couldn't make that trip without losing huge amounts of energy as heat. But AC voltages could be easily stepped up or down. This allowed for high-tension transmission, making it super economical to send power over vast distances before stepping it back down to a safe, usable level for your home.
Okay, moving on to Section 2, Anatomy of the AC wave. Let's figure out how we actually measure this oscillation.
Understanding AC can be kind of tricky at first. Think of it like water in a pipe being pushed aggressively forward and then violently pulled backward over and over. Because AC oscillates symmetrically between positive and negative, its average current over a full cycle is mathematically exactly zero. But wait, if the average is zero, how on earth does it boil water in your kettle? Well, the energy dissipated as heat is always positive, so engineers use a really clever standard called root mean square, or RMS. It's essentially a workaround to find the equivalent constant DC heating power of that sloshing AC wave.
To see how this math translates to everyday life, just think about that standard 220-volt outlet in your house. That 220 number is actually providing the RMS value. In reality, the true peak voltage of that wave is secretly spiking all the way up to 311 volts. This rapid, intense oscillation answers a super common student question. If the voltage hits zero, why don't our home light bulbs flicker? Well, the frequency of these cycles is just so incredibly fast, dozens of times every single second, that the steady RMS heating power keeps the bulb glowing completely continuously.
Let's hit Section 3, the language of phasors. We need a way to visualize time and amplitude without getting a headache.
So, to map out these rapid oscillating waves without getting totally lost in complicated math, enter the phasor. Think of the phasor as our visual Rosetta Stone. Just imagine the hand of a clock spinning backward. That's a phasor, a counterclockwise rotating vector. The actual length of this arrow represents the peak amplitude of our wave, and its rotation represents time progressing forward. We can track the exact instantaneous value of a wave just by looking at the vertical projection of that arrow as it spins. It literally turns messy, complex trigonometry into a simple spinning circle.
Right, on to Section 4, Components and Phase Races. Let's see what happens with resistors, inductors, and capacitors.
Now let's move to the actual physical hardware. Every single component on the power grid responds to alternating current a bit differently. They either keep the current and voltage perfectly in step, or they create what we can think of as a phase race, basically causing the current to either lag behind the voltage or lead ahead of it. Let's break these down one by one. It's actually pretty cool.
First up, think of a pure resistor, like the glowing heating element in your home space heater. This is our baseline circuit. Here, Ohm's law works exactly like it does in a basic DC circuit. Voltage and current are perfectly tied together in this phase race. They hit their zero, their minimum, and their maximum values at the exact same time. And because they cross the finish line together, they completely maximize the average power dissipated as actual, usable heat.
But things get a little weird when we introduce a coil, known as an inductor. You'll find these in the motors of your blender or your refrigerator. An inductor inherently opposes any changes in current through self-induced Faraday EMF. It basically acts like a drag. This drag delays the current, meaning it lags behind the voltage by exactly 1/4 of a cycle. And because they are out of sync, the average power supplied over a complete cycle ends up being zero. We call this a wattless current. It's sloshing around in there, but it's not doing any real work. On the flip side, let's look at a capacitor, like the ones that give your camera flash its quick, bright burst of energy. A capacitor stores charge on two separated plates, and it needs charge to physically flow before voltage can even build up across those plates. Because of this requirement, the current actually wins the phase race. It arrives early, leading the voltage by 1/4 cycle. But just like the inductor, because they are totally out of sync, the average power dissipation is once again 0.
So the absolutely crucial takeaway from this section is the stark contrast between in-phase and out-of-phase relationships. In-phase resistance does the actual heavy lifting. It does the real work in your home appliances. Out-of-phase reactance, however, creates this phantom, zero average power that just oscillates back and forth without doing any useful work at all.
Which brings us to Section 5, synthesizing the LCR circuit. What happens when we put all these pieces together? Let's find out.
When a resistor, an inductor, and a capacitor are all wired together in a single sequence, a series LCR circuit, the exact same current flows through all of them. However, because we just learned they all handle phase totally differently, the voltages across them end up pointing in completely different directions. We can't just add them up like ordinary numbers. The inductor's voltage points up, the capacitor's points down, and they literally fight each other, directly subtracting from one another.
To handle that fight, engineers do something really clever. They turn complex algebra into simple geometry. By mapping the resistance on the horizontal axis and the net difference of the competing reactances on the vertical axis, the total opposition to the current, which we call impedance, or Z, simply becomes the hypotenuse of a right triangle. The angle of this triangle tells us exactly how far the total current leads or lags the voltage.
And what's totally amazing is that this exact math is how you tune an old-school radio. An antenna picks up thousands of frequencies simultaneously, but by physically turning a dial, you are changing the capacitance. When you hit the exact resonant frequency where the inductive drag perfectly cancels out the capacitive lead, the opposing forces drop to 0. Impedance drops to its absolute minimum, and boom, you get a massive current spike for only that specific radio station, effectively tuning out all the others.
Finally, we've arrived at Section 6, transformers, the absolute engine of our grid.
Let's take everything we've learned and apply it to the massive machines safely bringing power to our homes. Out on the actual grid, true efficiency is measured by the power factor, which is the cosine of that phase angle we just looked at. If a grid has way too many inductive loads, like giant industrial factory motors, the phase angle gets large, drawing massive amounts of that wattless current we talked about. It does no work, but it still causes horrible heat loss in the transmission wires. To fix this, grid engineers have to constantly add parallel capacitors to neutralize that lagging inductive current, bringing the power factor back toward perfect efficiency.
To avoid energy loss over those incredibly long distances from the massive power plant to your specific neighborhood, we rely heavily on transformers. This is the very technology that won Tesla and Westinghouse the current war. A transformer uses mutual induction between two coils. By simply changing the number of turns in the wire coils, generators can step the voltage way up for travel, which reduces the current and cuts heat loss, and then step the voltage safely back down at a neighborhood substation before it reaches your home, where your circuit breakers stand guard to protect your delicate devices from any sudden surges.
But listen, while the math is perfect, physical reality is a constant, thrilling challenge. Even the absolute best transformers suffer from small energy losses that manifest as heat. Engineers have to meticulously design these giant metal beasts, fighting an ongoing battle against physics. They use thick wires for high current loops to combat copper resistance, and they actually slice the iron cores into incredibly thin laminations to stop swirling heat-generating eddy currents induced by the alternating magnetic flux. It's just an awe-inspiring effort to engineer away these physical losses.
It is an incredible, invisible symphony of physics happening in the wires above our heads right this very second. From the massive power plants miles away, down to the essential grounding wires that safely direct rogue electrical currents away from your family, alternating current really is a marvel of human ingenuity. But it does leave us with a provocative thought. As our modern world pivots toward new, modern green energy sources, how will we continue to tame and balance this delicate harmonic motion as our energy needs inevitably grow? Think about that the next time you plug in your phone. Thanks so much for joining me on this explainer, and keep learning.